All right, this is 14.2, Euler paths and Euler circuits. So what you'll learn in this section is you'll understand the definition of an Euler path, you'll understand the definition of an Euler circuit, you'll use Euler's theorem, you'll solve problems using Euler's theorem, and you use Fleury's theorem algorithm to find possible Euler paths and Euler circuits. All right, so definition. An Euler path is a path that travels through every edge of graph once and only once. Each edge must be traveled and no edge can be retraced. We know that names of vertices separated by commas can be used to designate paths, as we've seen in 14.1. And as we discuss Euler paths, you can use a pencil to trace these paths. And we also can indicate a starting vertex and number of the edges to illustrate Euler paths. For example, in this graph below here, we can use the Euler path going from A to B to E to F to D to B to C to E to D to G. And what it looks like is we're going to go from, if we look from A to B, we have that. And so, we're going from down here, A to B, B to E, E to F, F to D, D to B, and B to C, C to E, E to D, and then D to G. So it ends here and started there and went through all the edges exactly one time. Okay. Now note this path is not a circuit because we didn't end and start at that same place. So that's kind of the key again. The path and the circuits aren't always going to be the same. But if you do have a circuit, it will be a path. All right, so if an Euler path begins and ends at the same vertex, it's called a circuit, like I was just mentioning. So an Euler circuit is a circuit that travels through every edge of graph once and only once. And like all circuits, an Euler circuit must begin and end at the same vertex. So an example of a circuit here is we're going to go from A to B, then B to E, and then E to F, F to D, and then D to B, B to C, C to E, E to D, D to G, and then G rather back to A. And so we began and we ended both at A, the vertex here. And notice that every Euler circuit is an Euler path. And like I said before, not every Euler path is an Euler circuit. All right, so now let's have Euler's theorem. So the following statements are true for connected graphs. Remember, connected graphs, you have to be able to go all the pieces, not too disconnected or anything. So if a graph has exactly two odd vertices, then it has at least one Euler path, but no Euler circuit. Now, each Euler path must start at one of the odd vertices and end at the other one. And if a graph has no odd vertices, basically they're all even, it has at least one Euler circuit, which by definition is also an Euler path. Now, an Euler circuit can start and end at any vertex. So it doesn't matter if they're all even, so it can start and end anywhere. Now, if a graph has more than two odd vertices, then it has no Euler path and no Euler circuit. So that's going to be a key is you always want to go and look at all the vertices, find out how many odds and evens there are, and then this will tell you kind of what you're looking for as far as paths and circuits. All right, so let's pause here and come back with a actual example.